Right, can you hear me? Can I have an indication that somebody can hear me? Yes and no. I've taken the board away, and thank you. On your screen, you will now see the table that you were working with, and we're just going to go through things on that table. I will show you the board when we answer the questions. But looking at the table right now, and I look at A, and immediately I see the double bond, which makes this an alkene. And if I count 1, 2, 3, 4, I can see that this is but1-ene. For B, we notice single bonds. So it is saturated alkane. There's a substitute, a methyl group on the second carbon. There's a bromine on the first. So we can see that this is 1-bromo, 2-methyl propane. We'll get back to that. If I look at the next one, and I look very carefully this time, there are no substitutes, but there are 2 branches. Okay, all single bonds. It's an alkane. If I count 1, 2, 3, 4, 5, 6, then my substitutes are on 3 and 5. If I start counting on the other side, 1, 2, 3, 4, 5, 6, my substitutes are on number 2 and on number 4. So there are 6 carbons. So the parent group is hexane, and is a methyl on number 2 and a methyl on number 4. So it would be 2,4-dimethyl hexane. Methanol, I look at the al and I see it's an aldehyde. I look at the next one, I see the double bond oxygen, the OH, that is a carbonyl group, that is an hydroxyl group. Together the 2 form a carboxyl group. There are 2 carbons, so it is ethanoic. Methyl methanoate. We've come across that before. 2 names. The methyl group comes from the alcohol, so it was made with methanol, and the methanoate comes from the carboxylic acid, so it came from methanol and methanoic acid, and those 2 formed my ester. So number 1 is an alkane, number 2 is number B is a halo alkane, number C is a branched alkane, number D is an aldehyde, number E is a ketone, number F is an ester. So if we look at the questions, wonderful. 1.1, can you recognize alkene? And D was the aldehyde. The IUPAC names, 1.2.4, B and C. We've looked at B, and we said that B was 1-bromo, 2-methyl propane. 1-bromo, 2-methyl, 1,2,3 propane. And then they wanted us to name C as well. So if we look at C, we named C early on, we numbered from this side. That's carbon number 1, 2, 3, 4, 5, 6, and methyl group number 2. So it's 2,4 dimethyl hexane. The next question, structural formula. Write down the IUPAC name. We'll do the structural formulas on the board now for D and F, but write down the IUPAC name of the carboxylic acid shown in the table. The carboxylic acid table, there's the carboxylic acid. We spoke about it earlier on. There are 2 carbons. There's the carboxyl group, 2 carbons, ethanoic acid. But now they want me to draw methyl and methyl methanoate. Let's just go onto the board. Let me show you the board. Back to the board. Right, let's go back to the board. and show you methanol. Right, methanol, 1 carbon. It's an aldehyde, so it's got a 4-mile group, and then the rule of 4, 1 hydrogen. So that is methanol. Then methyl methanol. What I do is I always draw my oxygen bleach first, and then I draw my methyl. There's my methyl. And my methanolate. So there's my methyl, and there's my methanolate. Right, so there's my 2 structural formulae on the board for you, and we will look at the next question. And before we go to lunch, we're just going to do tea. We're just going to look quickly at what is represented in this table. Before we even look at the questions, we're going to look at the table and we look at what is represented. Alright, so what do I see? I start with A and I see a double bond. So this is an alkene. How many carbons? 1, 2, 3, 4, 5, 6. So the parent group, that being the longest chain, is X. And it's a hexene because of the double bond, and it's connected to the second carbon. So X2ene is the parent group. 2 methyl groups, so it's a dimethyl. 2 methyl substitutes. And remember, the numbering starts over here. Even though these are closer to that side, the double bond takes preference. So that's carbon number 1, carbon number 2, carbon number 3. On carbon number 4 there's a methyl. On carbon number 5 there's a methyl. So this is 4,5 dimethyl X2ene. Let's look at B. When I look at B, I immediately see a carbonyl group. Okay? Carbonyl group, ketone. How many carbons? 1, 2, 3, 4. Okay, so that being there, that being any different, it can't be on the first carbon because otherwise it wouldn't be a ketone, it would be an aldehyde, so this is definitely a ketone. So that, now if I look at that, if that was over there, it's the very, very same thing. And I remind you again of what I said yesterday, if we lift it off the page, and I turn it around and I switch it over and put it back on the page, then that would be on that side, but it's the same molecule. So, we don't have to indicate this carbonyl group. If you do, that is quite okay. We're not going to mark you wrong in the exam. So, you could have, this could just be 1, 2, 3, 4. This could just be butanone, or it could be butane 2-one, because it's on carbon number 2. Both is acceptable. So this is your first look at what is called, if you look at number C, this is your first look as what is called a condensed structural formula. So if you look over here, if you look at a carbon in A here, the one that I'm pointing to, that carbon has 3 hydrogens, so an end carbon has 3 hydrogens, and that's why you see this CH3 over here. So that CH3 as it is over there represents that part of the molecule. If there is a single bond between carbons, then an adjacent carbon would have 2 hydrogens, like indicated here by B. So that CH2 over there would indicate something like that. So clearly, there is an end carbon, there's a CH2, there's another CH2. As soon as you have a double bond, then the carbon can only accommodate one hydrogen. For example, if we look at this molecule on A again, there's a CH, there's the double bond, there's a CH. That is exactly what we have here. There's a CH, there's a CH, double bond in the middle. And that is the end carbon, so it has CH3. Right, so this is what we call a condensed structural formula. This is a structural formula. This is your first exposure to a condensed structural formula. As you can see, it is exactly as these structural formulas. You just have to picture it in your mind. Right, so carbon number 1, carbon number 2, 3, 4, 5, 6. So this is a hex. And there's a double bond, and the double bond is attached to carbon number 2. So this is H2E. Thank you. Let me just... Right. Sorry, you would have seen the document. I will look at it again, and I'll start with A again because I was on the board and I didn't show you the document. I'm going to go on to number D. As you can see over there, number D, pentyl propanoic, that would be an ester. Number E, if I look at number E, that is the longest chain as indicated over there. Notice there's a bromine over there, and then, yeah, that's the only substitute. So this is a substituted alkane, which makes it a haloalkane because of the substitutes. This is also called saturated. Notice there's only single bonds between carbons. Single bonds between carbons are called saturated. If there's a double bond between carbons, it's called unsaturated. This is an alkyne because of the triple bond. Just to show you again, if you look at number C is a condensed structural formula. I remind you again, the CH3 at the end over there is that CH3 over there, that's what that looks like. A CH2, that is what a CH2 looks like over there. So that would be an end carbon, that would be one attached. There's another one of those attached. So it's a CH3, CH2, CH2. And then when you have a double bond, there's only place for one hydrogen. That is what you see over there. Double bond, only one hydrogen on each carbon. That is what's indicated over there. And then of course the CH3 at the end, that's a CH3 at the end. So that gives you CH3, CH, CH, CH2, CH2, CH3. There are 6 carbons, 1, 2, 3, 4, 5, 6, X, and the double bond on the second carbon, X2E. Okay, right, so what are we going to do now? It's at 11. We will work through the rest of this worksheet as we go on. So it's break. You can go to break. We'll be back at about 11:30. Thank you. Right, we're back from break. Can I have an indication that people are back from break?
It's still working. Oh, okay. Is it a break?
Yeah, the break is over.
It's over.
Yeah, the break is over now.
And you're back again.
I'm back again.
Oh, okay. No, wait. He's back again.
Right, can I have an indication that break is over? And we are on break? Just on the chat quickly. Okay, wonderful. That's wonderful. So what we're going to do now is we are busy with the second worksheet. I'm going to give you 10 to 12 minutes to do question 2. We've looked at the table. Just answer the questions for me and then I'll go over the answers. That's the way we're going for the next hour or so. We're going to answer all these questions. We're going to consolidate our knowledge. You're going to do this one. I'm going to go through the next one with you. And then you'll do the next one and so on. So you've got 12, let's say 12 to 15 minutes to quickly just answer the questions based on the table that we went through just before. I'll put the table on the screen for you, then you can see the table. I'll give you 2 more minutes. Right, and we continue. Right, so on the table we're looking for, write down the letter that represents an alkene. So there's more than one alkene, as you can see it's 2 marks and it says alkenes. So an alkene has a double bond between adjacent carbons, and I see that A has a double bond between adjacent carbons. Just to show you, there's a double bond between adjacent carbons. So A is definitely an alkene. There's a double bond, but it's not between 2 adjacent carbons. There's a double bond between adjacent carbons, so our 2 alkenes is A and C. I have seen in exams that learners choose that as an alkene because of the double bond, but that is a carbonyl group, and that represents a ketone. Right, that being said, the next question is, which one is the ketone? I look for the carbonyl group, I find it, and compound B is a ketone. The next question, a compound with the general formula CnH2n minus 2. We saw that yesterday. CnH2n minus 2 is an alkyne, and an alkyne has a triple bond. We look for a triple bond between adjacent carbons, and we see that F has a triple bond between adjacent carbons. This question comes from 2013, and in 2013 we did cyclic compounds. Cyclic compounds are no longer, is not in the CAP syllabus, so we don't have to worry about 2.1.4. The IUPAC name of compound A. Let's look at compound A again. There's compound A. The longest chain is 1, 2, 3, 4, 5, 6. That is 6 carbons. And there's a double bond, so it's an alkene. So it's X something in. So if that is carbon number 1, carbon number 2, then this is X2 in as the parent chain. However, we've got two substitutes, a methyl group over there and a methyl group over there. And since that is carbon number 1, carbon number 2, carbon number 3, on carbon number 4 there's a methyl, on carbon number 5 there's a methyl. So the name is 4,5 dimethyl X2E. So that is 4,5 dimethyl X2E. Right, then we have to name number E. If I look at number E, the longest chain is that chain over there. And if I look very carefully, there's a bromine over there, a bromine over there, and a methyl over there. Counting the number of carbons, 1, 2, 3, 4, 5, 6, 7. And 7 carbons is heptane, because there's only single bonds. So if that was a hydrogen, that was a hydrogen, and that was a hydrogen, then this molecule would have been heptane. Okay, so heptane is the parent group. And if I number 1, 2, 3, 4, 5, 6, 7, then on carbon number 1 there's a bromine, on carbon number 2 there's a bromine, and on carbon number 5 there's a methyl. So, in alphabetical order, the 2 bromines go first. So it's 2,3 dibromo 5 methyl heptane. Okay, 7 carbons is heptane, 8 carbons is octane, 9 carbons is nonane. The list was given to you yesterday by Kashif. Right, and then we have to name number F. There's number F, that is the longest chain. There's a methyl substitute, but the longest chain is 1, 2, 3, 4, 5. So it's a pent, and there's a triple bond and an ion. So we need to look where the triple bond is. Carbon number 1, carbon number 2. So the triple bond is on carbon number 2. So the parent group is pent 2 ion. And since this is carbon number 1, 2, 3, 4, there's a methyl group on carbon number 4. So it is 4 methyl pent 2 ion. Right, next question is, compound D is prepared by reacting two organic compounds in the presence of an acid catalyst. Compound D. Okay, there's compound D, and compound D, as we can clearly see, is an ester, because it's got a methyl group and an OH group. Clearly from the name, we can see that that part of the name comes from pentanol, because remember, it is only primary alcohols that forms the esters. So it's pentan-1-ol, and this comes from propanoic acid. So, and that's how we got pentyl propanoate. Remember the catalyst that we use for esters? The catalyst that we use for esters is sulfuric acid. So let's look at the questions. The homologous series to which D belongs. D is definitely an ester. Structural formula of compound D, I will do on the board right now after we've answered the next 2 questions. The IUPAC name of the organic acid used to prepare D. We've discussed that, and we said that the propanoate part comes from the organic acid. So the organic acid is propanoic acid. The name or formula of the catalyst used. We've spoken about the catalyst. It is a sulfuric acid. That is the name, and the formula is H2SO4. So let's show you the board, and let me draw right. There's the board, and and I'm going to draw pentyl propanoate for you. So I'm first going to write down the name, pentyl propanoate. We know that the pentyl group comes from pentan 1-ol, and the propanoate comes from propanoic acid. We know this now because we learned it this morning. Right, so pentyl 1, 2, 3, 4, 5, and that's my alkyl group. Oxygen bridge, and then from the propanoic acid we've got our carbonyl group, and there must be 3 carbons. And there we have it. There's the oxygen bridge, there's the pentyl, and this is the propanoic part. Right. So that is our ester, pentyl propanoate, and I remind you that the pentyl part comes from the pentan 1-ol, and that the propanoic part comes from the propanoic acid. Right, so if we move to the next worksheet, which is on page 6 of 10, I'm going to work through it with you, give you a break, and then you can do the next one after that. For those of you, it's just 30 seconds or so, just if you need to write down the ester from the board. Right. Okay. And this is Metro Simplification District, September 2010, and I draw the molecule on the board A, and it says CH3, C, triple bond with another C, and I look at it, and I see that this particular molecule in this has a mistake. Can you see the mistake? Let me just show you quickly. There's a mistake on this question, just to show you what the mistake is, because we've learned. Show you the molecule again. When we look at this molecule, I wrote the CH3 on the board, I wrote the C on the board, and we notice that this particular carbon, for some reason or other, has 6 bonds. Can you see that? There's the carbon, there's 3 bonds over there, 4, 5, 6. Now that is impossible because of what I told you yesterday, the rule of 4. So that is an error in MCED 2010. I don't know if they picked it up, but definitely that is incorrect. So what I'm going to do, I'm going to take that CH3 over there, and that CH3 over there, and I'm going to move it over to the next carbon, and then take those 2 H's away so that we can have a proper triple bond, because it's impossible to have substitutes there and there if you've got a triple bond over there. Okay, right, so if I move that there and there, Let me just show you the board again. So there's a triple bond over there. And as you can see, I'm going to go there and I'm going to move my CH3 over there and my CH3 over there. So I can't have any more attachments over there because of that triple bond with that. Right. Then on the next carbon there's another CH3. And then there's a CH3 over there and an H over there. So all I've done is I've moved those over there to make the molecule more scientifically correct. So if I look at this molecule on the board over here and I have to name this molecule, then what takes preference is the triple bond. So it's definitely an alkyne. So I've got 1, 2, 3, 4, 5, 6. So the parent group is X. I, and I've got to put the number in there. That's attached to carbon number 2, that's carbon number 1, that's carbon number 2, 3, 4, 5, 6. The reason why that's carbon number 1 because we want the triple bond to have the lowest number. If I made that carbon number 1, it would be attached to number 4. So this is definitely H2I, that's the parent group. Then I've got methyl, 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 3 methyls. 2 on number 4 and one on number 5. So it is 4, 4, 5 trimethyl H2I. So that would be the IUPAC name for scheme. Right, so that would be the IUPAC name for that particular molecule. The next question relates, write down the structural formula for compound C. The structural formula for compound C. I'm going to write the name down first. 2-methyl pentanoic acid. Right. This is very, very common. This particular question is very, very common in the exam. So, my parent group is pentanoic acid. That is quite easy. 1, 2, 3, 4, 5. And we normally draw the pentanoic, the acid part on the right hand side. Right. Most importantly, the functional group is on the right hand side. That is carbon number 1. Okay? That is carbon number 2, that is carbon number 3, that's carbon number 4, that's carbon number 5, and my methyl group is right next to it. So that is 2-methyl. And there's my carboxyl group. Okay, and in the rule of 4 we put in our hydrogens. And then we have 2-methyl pentanoic acid. One of the mistakes that learners make, for some reason or other, because we read from left to right, they want to name the carbons always from left to right. However, the rule says we number so that the functional group has the lowest number. So you always number so that the functional group has the lowest number. So in this case, that is the functional group, so it has to be carbon number 1. In this case, that is the functional group, and that's why I started numbering from that side. Right, so our next question is, write down a structural isomer of B. Okay, a structural isomer of B. So let me draw B first, and then we can look at structural isomers. Right. So B, CH3, CH, double bond carbon, CH3, CH3. Right, so, when we look at that, when I look at structural isomers, I immediately start counting. And I count 1, 2, 3, 4, 5. So that is C5. Let's count the H's. 3, 4, 7, 10. H10. Now when I look at C5H10, I immediately recognize that it is an alkene CnH2n. So if I draw, I can draw 5 carbons, and it doesn't matter where I'm going to put the double bond, it's going to work. So if I put the double bond over here, and I put single bonds for the rest, and I use the rule of 4, I'm going to get, that's 2, that's 3, that's 4, that's 5, 6, 7, 8, 9, 10. And this structure is totally different to that structure. So it's an isomer. Let's see what happens if I move that double bond. Let's move the double bond over there. Put in my single bonds and use the rule of 4. 1, 2, 3 hydrogens over there. 1 hydrogen over there. 1 over there. 2 more over there. 3 over there, and if we add them up, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all of these is C5H10. Obviously, if I move that double bond over there, it will be the same, because if I lift that molecule, flip it over, put it back on the board, it will be there. If I take that double bond, put it over there, it's the same molecule, same thing, flip it off the board, rotate it, put it back on the board, it will be there. So these are the possible straight-chain isomers for that molecule. Okay, and this would be pent 1-ene, and that would be pent 2-ene. So they are both possible isomers. They ask you to write one isomer, and there's possible isomers. The other option would be, see the double bond over here? If I move it over there, it can also work. If I move it over there, it can also work. And once I move it and I put in my hydrogens, I will get C5H10 every time. They just wanted one isomer. There was 4 possibilities of a correct answer in that case. The next question, give the homologous series to which D belongs. 2-methyl pentanoic acid. Now that's C, the homologous series. Now, again, you're getting used to condensed structural formula. So what I'm going to do, I'm going to suggest that while you're getting used to it, you draw the condensed structural formula, and then you draw the structural formula, and then you make a decision. You're not in a hurry at this stage. Okay, so my condensed structural formula, as on the question paper, is CH3, CH2, COO, CH2, CH3. Right, so that is my condensed structural formula. I start on the left-hand side, and I go C, and there's my 3 H's. And as attached is another C, there's my 2 H's. Attached is another C. Right? double bond oxygen, oxygen, CH2, CH3. So, something that we need to get used to is this. When you see that in the middle of a molecule, two oxygens looking at you, then you know it's an ester. Okay? So if I now have to give the IUPAC name, this is the structural formula, that's a condensed structural formula. There's my oxygen bridge, there's my alkyl group, and there's my OH. Right, so, alkyl group first, ethyl. 3 carbons, propanoate. Right. Give it some time to absorb that knowledge. Right. Give the general formula of the homologous series to which E belongs. Right? The general formula of E. Right, that's something new. We've got general formulas for alkenes, alkanes, and alkynes. I'll just draw E on the board and we'll analyze it. CH3, CH2, CH2, OH. Okay. Right. Now, what I want to show you, if it's CH3, then it would have been propane, and the formula would be CnH2n plus 2. That would be the general formula of an alkane. One of the H's, the third H over there, has been substituted by an OH. So there is still 2n plus 2 H's, but there's also an O. So it is, for an alcohol, it is almost exactly the same as an alkane, only the difference CnH2n, and there's an O. Are we clear? Look at the propane. See the 3 hydrogens over there. See the 2 hydrogens over there. The OH is substituting one of those hydrogens. So there's still H, which means it's still 2n plus 2, but it's also an O. And that's why you have, sorry, 2n plus 2, O. Same number of hydrogens, like over there, but an extra O. Okay. Give you some time to absorb that knowledge. Okay.
That was one. Some of the others might jump, she couldn't get onto the reader.
Okay. Right, so we move on and we now have to draw the structural formula for compound F. So if you look at compound F, my laptop doesn't want to. No, because my laptop is problem. Okay. So it's 2,3 dimethyl pentanal. So pentanal, 1, 2, 3, 4, 5. Pentanal, it's an aldehyde. So I've got the 4-mile group. And on carbon number 2 and on carbon number 3, we have a methyl group. So this is carbon number 1 because this is the functional group, the 4-mile group. On carbon number 2, there's a methyl. And let's draw this on the side. On carbon number 3, there's another methyl. It does not matter whether we draw the methyl group on this side or on that side. At this particular moment in time, it makes no difference. We know at university they can speak about cis and trans. This is trans. This is something for you to remember if you're going to study further. And if they're on the same side, it would be cis. We don't need to, for those of you that are over interested, I'll tell you that at this stage, it doesn't matter whether we draw them cis or trans. Okay, so that is 2,3 dimethyl pentanal. That is an aldehyde. Okay, so we've done the first 3. So for number 4, 16 marks, I'm going to give you 13 minutes to do on the worksheet, page 7 of 10, question 4. So I'm going to give you 13 minutes, and you do question 4, page 7 of 10. Right, we're back. We've lost the Google Meet learners again. Right, page 7 of 10. Write down the letter that represents the compound that has a carbonyl group as its functional group. So the carbonyl group, I look at it and I see that is A. So A has a carbonyl group. The carbonyl group is C double bond O. Right, the letter that is a ketone, that is also it is also a carbonyl group, a functional isomer of A. A functional isomer of A. So isomer is an isomer has exactly the same molecular formula, and it has a different structural formula, and it is also a different functional group. So you draw A, and then I'm going to show you quickly on the board the functional isomer. So I'll also introduce you to a functional isomer now. So when I draw A, I've got 4 carbons, double bond on the 4th carbon, double bond oxygen on the 4th carbon. And like I said, when we speak isomer, I start counting. I've got 1, 2, 3, 4, 5 carbons. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nitrogens. And I've got an oxygen. Right, so that is the molecular formula for, in this case, pent and 2O. The carbonyl group being on the second carbon. Right, so let me draw number E for you. Number E is pentanal. So pentanal is 1, 2, 3, 4, 5 carbons, and on the fifth carbon there is a 4-mile group. And the carbonyl group and the hydrogen is the 4-mile group. Right, so let's start counting. 1, 2, 3, 4, 5, that is correct. Let's start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that is correct. And there's an oxygen, that is correct. So, both of these have the same molecular formula. However, this one has a carbonyl group and is a ketone. This one has a 4-mile group and is an aldehyde. And because they are different homologous series, they are different functional groups. They are called functional isomers. Because the one is a ketone, the one is an aldehyde. They are different types of organic compounds, but they have the same molecular formula. So a functional isomer, same molecular formula, different structural formula, but also different functional groups, and therefore they are called functional isomers. 4.1.4, write down the letter that belongs to the compound, write down the letter that represents the compound that belongs to the homologous series with general formula CnH2n. CnH2n, that is an alkene, and our alkene on show is number D, which is butene. The IUPAC name for compound C, 4 carbons, on the second carbon there's a methyl, so that is 2-methyl butane. IUPAC name of compound F, there are 3 carbons, you can see there's a carboxyl group, and that is propanoic acid. Right, and then they're looking for a positional isomer of compound D. So we look at compound D, butene. Let me just draw butene. So we've seen functional isomers now, different functional groups, same molecular formula. Now we're looking for a positional isomer. Right, so butene. Bute is 4 carbons, and on the second carbon there's a double bond. I put my single bonds in. Rule of 4, 1, 2, 3. There's 3 bonds, 4. There's 3 bonds, 4. So that's butene. So positional. They speak about the position of the functional group. So there's your functional group on carbon number 2. If I move it to carbon number 1, and we start counting again, because it's an isomer, we count, we double check, we see C4. And we start counting 1, 2, 3, 4, 5, 6, 7, 8, H8. Let's check. 1, 2, 3, 4, that is correct. 1, 2, 3, 4, 5, 6, 7, 8, that is correct. So, those are positional isomers. Positional isomer because the position of the double bond is different. Write down the structural formula of B. Okay, let's look at the structural formula of B. The structural formula of B. B is 1,2 dibromoethene. So let's just draw the T, double bond C because of the ethene. And let's just, 2 bonds can form still. And let's put in our dibromo. And our bromos is on number 1 and on number 2. And the others have to be H's. And that is 1,2 dibromoethene. Structural formula for compound D, butene. We've drawn butene 1, 2, 3, 4, double bond, and that would be butene. Right, so that is butene. Then number 4.4, write down the homologous series to which E belongs. The homologous series to which E belongs is an aldehyde. Name the functional group of compound E. Compound E, the functional group for an aldehyde is the 4-mile group. We need to see the 4-mile group for it to be an aldehyde. So that is the structure of the 4-mile group, and the name is a 4-mile group. Right, so we move on. Question 5. Right, so for question 5, all the questions pertaining to G. Now G, what you see there in G, is a polymer. So all the questions pertaining to G, we cannot answer at this particular moment in time. So we cannot answer question 5.5. So I expect you to answer question 5.1, 5.2, 5.3, 5.4, 5.6, 5.7, and 5.8. Right, so you can start, and I'll give you 12 minutes again to do question 5, and then I'll go through it with you. Right, so we're back, and I see we've got about 2 minutes before lunch, so we'll just answer the first two questions and then we'll move on to lunch. So our first question is, identify the haloalkane from the list of the organic compounds. Write down only the letter of the appropriate compound. When I look at the list that we've been given, I look and I immediately see that for C, there's a chlorine and there's a bromine, and these are all single bonds, so that is a haloalkane. So the answer there is C. 5.2, one of the compounds from the above list is an alcohol. Write down the type of alcohol. Select from primary, secondary, or tertiary. So if we look very carefully, there's propanoic acid, there's butanol, that is an aldehyde, that is a carboxylic acid, that is a haloalkane, that is an alkene, that is a ketone because of that oxygen over there, there's my alcohol. Notice my OH group, which is the hydroxyl group, is attached to a carbon that is attached to one other carbon, so this is a primary alcohol. If that OH was over here, then it would have been on a carbon that is attached to two other carbons, it would have been secondary, but this particular one is a primary alcohol. 5.3, write down the letter of the functional isomer A. A is butanol, 4 carbons. I've shown you before the aldehyde, and there we go, the ketone, 1, 2, 4 carbons, so this is butan-2-one, that is butanol. Two different functional groups, but aldehydes and ketones, if they have the same number of carbons, are functional isomers. So it is 12:45, it's 1:45, you're going to lunch now, and you'll be back at 1:15, and then we'll complete this worksheet, and then we'll move on to intermolecular forces. So I'll see you at 1:15. Right, so we're back. Can I have an indication that everybody's back? Just a little note on the chat will tell me that you're back. Okay, I'm glad you're all there. Right, so when we stopped at 5.3, 5.4. Give the IUPAC names for the following compounds. Compound C. Compound C, if we look carefully at compound C, we see the longest chain is 1, 2, 3, 4, 5 carbons. We have a methyl on that carbon. We have a chloro on the middle carbon. We've got a bromo on that carbon. So, if we start numbering, 1, 2, 3, 4, 5, it is 2 bromo, 3 chloro, 4 methyl, pentane. So C is 2 bromo, 3 chloro, 4 methyl, and there's all single bonds, so it's pentane. Right, the next one is compound H. Now compound H, you've got to be careful, because on face value, it looks like there are 4 carbons. But on the last carbon, there's a CH3. So in actual fact, the longest chain is 5 carbons. Okay, so the 5 carbons go up to there, which means that is a substitute, that is a substitute, that is a substitute. So it is, counting from the left, 1, 2, 3, 4, 5. I've got 2, 2, 4, trimethyl pentane. So just be careful. They like doing this, putting a CH3 over there. That means there's an extra carbon. So the longest chain is not 4 carbons, but 5. So look out for that in tests and exams. Examiners love doing that to you. Right, we can't answer 5.5. I explained to you earlier on, compound G is a polymer and we haven't done polymerization yet. Then let's define a chain isomer. So I'm just going to go to the board and speak about, we've spoken about a positional isomer. We've spoken about a functional isomer. We're going to now speak about a chain isomer, and those are the only 3 types of isomers. So let me just show you the board. And then speak about a chain isomer. Right, so a chain isomer. Now, if we take butane, 1, 2, 3, 4, 5 carbons. We notice that butane, and when I speak about isomers, I said we must start counting, and I see 1, 2, 3, 4, 5 carbons, and if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens, okay, that is butane. But let's have a look at 4 carbons with a methyl. Let's see if it is an isomer. Put in our hydrogens, rule of 4. Right, so carbon makes 4 bonds. 4, 4, 4, 4, 4, it's all 4 bonds. and let's start counting 1, 2, 3, 4, 5 carbons. That is correct. And we start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Definitely those are isomers. Okay, so they are both C5H12, the chain length is different, and hence the word chain isomers. Right, so there is a 5-carbon chain, there is a 4-carbon chain, the chain length is different, hence the word chain isomers. So there are 3 types of isomers. Number 1, we saw earlier on today where the position of the double bond changed. Those are positional isomers. Then we saw functional isomers. Isomers, same molecular formula, different functional groups, aldehydes and ketones. Number 3, chain isomer. Here, the chain length changed. Right. Draw the formula of a chain isomer of D. So D, so let's look at D. If I look at D, 1, 2, 3 carbons, double bond, hydrogen, hydrogen. Alright, so the chain length is 3. Okay? With a methyl substitute. And all I'm going to do is make the chain length 4, keep my double bond at the end, and then we have a chain isomer, different chain length. Let's double check and count. C4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, H8. Double check, 1, 2, 3, 4, that's sorted. 1, 2, 3, 4, 5, 6, 7, 8, that's sorted. That is a chain isomer. This is 2-methyl propene, and this is but 1-ene, chain isomers. Right. Draw the structural formula, the action equation for the production of an ester when 2 compounds of the above list reacts. Right. 2 compounds of the above list reacts. To form an ester, we need an alcohol and a carboxylic acid. Let's find our alcohol and carboxylic acid. Right, so our alcohol is propanol. So let's draw our alcohol. There's our alcohol, propanol. There's our alcohol. And we're reacting it with a carboxylic acid. And our carboxylic acid is propanoic acid. So let's draw propanoic acid. We know the story. The OH from the alcohol and the H from the carboxylic acid forms H2O. And our ester, let's throw the H2O at the bottom of here so that we can make place for the ester. Our ester is when that carbon joins that oxygen. So we've got 1, 2, 3, and that is from the alcohol. And that joins up with the oxygen over here, which is attached to a carbon, double bond oxygen, and then 2 C's. Right. Only thing that is missing is that over the arrow we show our sulfuric acid catalyst. Right, sometimes the mark is awarded for the sulfuric acid catalyst, sometimes it's not. I suggest you put it in anyway. Okay, so it was propane 1 mole, propanoic acid, and it's propyl propanoate. Okay, so that is enough consolidation for the day. There's some extra questions that your teachers can go through. There's still question 6 and question 7. What I want to chat to you about now is intermolecular forces. I'll try and get through as much as I can, because we want to stop at 20 past 2. Right, so our intermolecular forces. Molecular forces. Inter means between. So it's forces between molecules. Right? Not forces inside the molecules, but forces between molecules. The first intermolecular force that I want to introduce you to is a hydrogen bond. Right, so what I want to show you is I want to look at the hydroxyl group. Now, the hydroxyl group has a bond between oxygen and hydrogen. And what is important with intermolecular forces is the concept of electronegativity. In my opinion, somebody who's been teaching science for 34 years, is that it is probably the most important concept in chemistry. If you understand this concept, it opens up then to many, many other concepts. It helps you understand this what says of the force with which the nucleus of an atom attracts a shared pair of electrons in a covalent bond. A measure of the force with which the atom attracts a shared pair of electrons in a covalent bond. So here's a covalent bond, and there's a shared pair of electrons in that covalent bond. What is happening is that this actual bond is held together by the electrons are negative, and the nucleus of an atom is positive. And we know that there's a force of attraction between a positive object and a negative object. So what is happening is that this shared pair of electrons is attracted to that nucleus. It is also attracted to that nucleus. And a tug of war develops between the two. And if pulling at really the same strength, then that bond will stay there forever. And that is called a covalent bond. So a pure covalent bond is very, very strong. It is an attraction between two nuclei pulling on the same shared pair of electrons. If there is a difference, for example, on the periodic table, that oxygen molecule pulls with an electronegativity equivalent to 3.5. These are relative strengths. An electronegativity of 2 is twice as strong has an electronegativity of 4. These are relative states. And for hydrogen, the electronegativity is 2.1. And the difference in electronegativity is 1.4. So the electronegativity difference here is 1.4. What that means is that the oxygen is pulling that shared pair of electrons with a much stronger force than the hydrogen is pulling that shared pair of electrons. So there's a tug of war and oxygen is winning. So what is happening is that the shared pair of electrons moves closer to the oxygen. That makes the region around oxygen negative. Not completely negative, there's still shear taking place, but it makes it slightly negative. Because this is further away, that becomes slightly positive. That is the small letter delta. Right. So, this is slightly positive, that is slightly negative. This is referred to as a positive dipole moment. This is referred to as a negative dipole moment. So, the oxygen forms a negative dipole moment because of its stronger electronegativity. The electrons are pulled closer to it, making that region slightly positive, pulling it further away from the hydrogen, making that region slightly positive. So this is a positive dipole moment, this is a negative dipole moment. Together, the positive and negative dipole moment forms a di, which means two poles. Positive dipole moment, which is the positive pole, negative dipole moment, which is the negative pole, and so we have a dipole. That results. Right, so electronegativity was important in us understanding the concept of what is a positive dipole moment, what is a negative dipole moment. Right. Just give you some time to write that down, and then I'm going to use that knowledge. Right. So, let's look at two OH molecules. There's one, and here's another one. So that is delta positive, that is delta negative, that is delta positive, that is delta negative. And we know that positives and negatives attract each other. So, between the positive dipole moment of the hydrogen and the negative dipole moment of the oxygen, a force of attraction can develop. And that force of attraction that is developed here, between that positive and that negative, is known as a hydrogen bond. Now what is important, and I've read many of our textbooks, what is important to understand is that a hydrogen bond is a dipole-dipole intermolecular force. There is a dipole, there is a dipole hydrogen bond. So the hydrogen bond are the strongest of the dipole forces. It is a dipole force. Right? However, these dipole forces only occurs when oxygen is bonded to nitrogen, when oxygen is bonded to when hydrogen is bonded to nitrogen, when hydrogen is bonded to oxygen, and when hydrogen is bonded to fluorine. So these are the only three elements that experiences hydrogen bonding. Okay? I call them the NOF elements. They are the only ones that experience hydrogen bonding. We in particular, for organic chemistry, are interested in that one. Because those are the ones that are present in alcohols. Okay? So, that is a hydrogen bond. And hydrogen bonds are very, very strong dipole intermolecular forces. There are other dipole forces which are much weaker, but hydrogen bonds are the strongest. Right, then, so if we look at an alcohol, so there is an alcohol. Alcohols has this OH, and that is a site. A site is a place where it can exist for hydrogen bonding. Right? And because hydrogen bonding, right? H bonding are strong intermolecular forces. And thus, the molecules to separate them from each other takes a large amount of energy. Right, so to break these two molecules apart from each other again will take a large amount of energy. So if we look very carefully, if there's another methanol molecule, then that would be a hydrogen bond. So alcohols have hydrogen because it has this OH molecules. Okay. Take that down. I'll give you a minute or two to take that down, and then I'll chat further. Right, so having looked at this and having looked at the alcohols, one can immediately assume that alcohols have strong intermolecular forces. Alcohols have relatively strong intermolecular forces because hydrogen bonds are strong intermolecular forces, and alcohols have hydrogen bonds, so alcohols have strong intermolecular forces, right? And therefore, it will take a lot of energy to separate these alcohol molecules from each other. Okay, let's have a look at the next thing I want to show you. Right, I'm going to wipe this from the board. And the next thing I'm going to look at is a carboxylic acid. So we've looked at alcohols, let's look at the carboxylic acid. Right, so carboxylic acid and that is methanoic acid, has a carboxyl group. Now carboxyl group consists of an hydroxyl group. Okay, I immediately recognize that. That is a site for hydrogen bonding. That's cool. Right? There's a shared pair of electrons, the oxygen is closer, that is delta negative, that is delta positive, and if another OH from another methanoic acid comes along, and there we go. Here's your hydrogen bond. Okay, so far, carboxylic acids have hydrogen bonds. There's something else. We've got this, the carbonyl group. The electronegativity of oxygen is 3.5, we know that. The electronegativity of carbon is 2.5. The electronegativity difference there is 1. So what happens is that the shared pair of electrons, in fact 2 shared pair of electrons, are pulled much closer, and that becomes delta negative. So theoretically, the carbon should become delta positive. However, This is slightly positive. There's a shared pair of electrons over there. There's a shared pair of electrons over there. And that moving slightly closer that way and slightly closer that way cancels out the positive with the carbon. So the carbon does not become slightly positive because of the other two covalent bonds sharing the impact of that electronegativity difference. So, what then happens is I have another negative dipole moment. And the beauty about it is, if another molecule comes along, then what happens is that the positive dipole moment created by the electronegativity difference between oxygen and hydrogen allows a positive dipole moment to be attracted to that negative dipole moment, and there we have another hydrogen bond. So, that means that a carboxylic acid has two sites for hydrogen bonding. So there's two places hydrogen bonding can take place in a carboxylic acid. So clearly, I've got to separate that molecule, and I've got to separate that molecule, and it's going to cost me more energy to separate the molecules of carboxylic acids than of alcohols. So carboxylic acids has stronger intermolecular forces than alcohols. Because separating the alcohols, I have to separate two molecules that has one hydrogen bond between them, separating the carboxylic acid molecules, and they have two hydrogen bonds, and it's going to cost me energy to separate the one and energy to separate the other. And as a result, carboxylic acids have stronger intermolecular forces than alcohols. And it would cost much more energy to separate the molecules of carboxylic acids than that of alcohols. So now, carboxylic acids is strongest, and then alcohols. Right. Let's look. Just give you a minute or two to write that down, and then we can move on. Right. Before I do the next one, I just want to remind you a little bit. As you notice, electrostatics is important. Attraction between positive charges and negative charges, repulsion between two positive charges, repulsion between two negative charges are important. I just want to remind you of something that you should have done in grade 10 called polarization. if I take something that is positively charged, and I approach a neutral object. Now, a neutral object has the same number of positives as it has negatives. So this object has 5 positives and 5 negatives. So when I bring a positive charge to it, then what happens is the positive charge will attract all the negative charges to the one side, leaving the positive charges on the other side. Notice there's still 5 negatives and 5 positives, like there was over here. So the object itself now is still neutral, but what I've done is I've created a negative end and a positive end. Okay, so it has been polarized. There's negative, positive. So polarization has taken place. And that is something that we learned in grade 10. And that is something that is important for the next discussion on intermolecular forces. So the next thing we're going to look at is an aldehyde. And an aldehyde, let's just draw an aldehyde. There's an aldehyde. There's my formal group. There's an aldehyde. And we already learned from looking at carboxylic acid that is slightly negative and the slightly positive disappeared over here because of the electrons that share the impact of that positivity. So I've got what we call a negative dipole moment. Now, if the negative dipole moment of one molecule approaches a neutral end, so what is happening here now is that this is totally non-polar. So this is non-polar. The electronegativity difference is minute. I think it's 2.5 and 2.1. The difference is 0.4. That is relatively small. That is relatively non-polar. So this negative dipole moment approaches the number end of a molecule. And exactly what I told you is, you see, there's electrons around here, there's electrons around here, there's electrons around this nucleus, there's electrons around those nuclei. They are all in constant motion around the nucleus. So what happens if a negative comes, it pushes the electrons to the one side of the molecule. Right? It pushes the electrons to the one side of the molecule, exposing the nuclei, which are positive, because that is where the positive protons are found, and it theoretically polarizes the non-polar end of the molecule. And by approaching the non-polar end, it theoretically polarizes and it creates, so the electrons all go to the one side and the positive end was formed. So what we are saying is that can induce dipole. In other words, it can polarize a non-polar end of a molecule. So it can induce a dipole in a non-polar end of a molecule. So aldehydes, right, would have dipole-induced dipole intermolecular forces. So it has dipole coming from the dipole moment, induced dipole. And that is important. So obviously it's not a hydrogen bond. The negative dipole moment had to do a lot of convincing for this intermolecular force to develop. So this is much weaker than a hydrogen bond. And it's much weaker than dipole-dipole intermolecular force. So far, we've got carboxylic acids being the strongest. Then we've got alcohols. So this has two sites for H bonding. This has one site for H bonding. And then we've got aldehydes. And that is dipole induced dipole. So intermolecular forces gets bigger that way. Right. The only difference, now notice, what I want to show you is that this positive dipole moment is exposed right around there. The surface area which covers that area. So this molecule can approach the negative end from any of that degrees of movement. And that is important. Why is it important? Because when we look at a ketone, and a ketone also has this carbonyl group, but the degree of exposure of that ketone, that's a negative dipole moment, is much less, comparatively speaking, to the degree of exposure of the other. Okay? So in other words, this ketone can only approach the non-polar end from one side. This could approach it from any other side, and the probability of a induced dipole intermolecular force developing is much greater in an aldehyde than in a ketone. So they both aldehydes and ketones have induced dipole forces, but because of the degree of approachability of that carbonyl group compared to that carbonyl group, the aldehyde intermolecular forces are much stronger than that of a ketone. Okay, so far we've heard of hydrogen bonds and we've heard of dipole-induced dipole intermolecular forces. Right. Give you an opportunity to think about that through, absorb, think about the knowledge, absorb the knowledge, and take it down, and then we'll move further. I know it's a lot, but we're almost at the end. We're almost at the end. As promised, I will stop at 2:20 for you. So you can have 10 minutes more of your holiday. I think it's funny because I'm working all week. Right. The last type of intermolecular force I want to tell you about is the weakest of the lot. So within a hydroxyl group or a carbonyl group, we can develop dipole moments, but if there's nothing, like, let's have a look at propane, butane. Okay? And then and we're going to compare it to methyl propane. Now we notice that these are chain isomers. They're both C4H12. They are chain isomers. And these molecules have no carbonyl group, no hydroxyl group. And when they come close to each other, they may or may not develop very, very weak intermolecular forces called London forces. Now let me explain to you what a London force is. So hopefully you're going to understand my explanation because you understand what an atom is. So an atom has a nucleus. And the nucleus of an atom has electrons orbiting the nucleus. And when it orbits the nucleus, it is in constant motion. So at a particular time, when there's a bunch of atoms, the scenario might occur where most of the electrons, because they are moving in these orbits around the nucleus, might find itself on one side of an atom because they're orbiting. So there's a nucleus, electrons going around the nucleus in constant motion, and if there's a bunch of atoms and the electrons are all moving, the scenario might exist where most of the electrons are on the one side of the molecule. And in that moment, when most of the electrons is in one side of the molecule, that side of the molecule becomes negative and the other side becomes positive. So for that moment, we have a negative end and a positive end. So for that moment, a dipole exists. We call this a momentary dipole. The electrons are in constant motion around the nucleus, which is positive. There's lots and lots of atoms, and all the electrons are moving, and the scenario can arise where most of the electrons are on one side of the molecule, leaving that side negative and the other side positive. But this happens just for a moment because the electrons are moving and they can move out of position again and their moment has passed by. However, if two molecules approach each other and it just so happens that at the time when they are close enough to each other, both the molecules exist as temporary dipoles, and intermolecular attraction can develop. Now the probability of this happening is very, very small. Fortunately, there are billions and billions and billions of molecules, and they can develop intermolecular forces. And if the molecule is bigger, in other words, it has a larger surface area, the probability that another molecule can attach at whatever end of that molecule is even bigger. So it's all about probability. So the weakest of the intermolecular forces is these temporary, some books refer to momentary dipoles. It's just for a moment. And then the electrons move out of position. But if two molecules in the same, that both have momentary dipoles, an attraction can develop between the positive and the negative end of the different molecules. Now, listening to the story, you think the probability of this happening is very small, and it is. And that is why these intermolecular forces are so weak. Because the probability of them happening is small. But what does help, if the molecules have a larger surface area, and then the points of contact increases because of the larger surface area. So larger surface area would give the molecules more space to make contact with each other, and the probability then increases that a momentary dipole between two molecules will develop. These very, very weak intermolecular forces are called London forces, also known as dispersion forces, also known as momentary dipoles, also known as temporary dipoles. But we will refer to them as London. So, with London forces, what we are interested in is the fact that a straight chain molecule has a larger surface area more contact points for London forces. And hence stronger intermolecular forces, my pen is also dry now, and more energy is required to separate it. Right, so London forces, larger surface area, more contact points, stronger intermolecular forces, more energy required to separate it. And here, surface area is smaller, less contact points. So, importantly, straight-chained alkanes has stronger INFs than branched alkanes. Right. And that those are the intermolecular forces. So, carboxylic acids, alcohols, aldehydes, ketones, and then the alkanes. Then we look at surface area when there's no carbonyl group or when there's no hydroxyl group to influence the strength of the intermolecular forces. So that was a lot of information. A lot of information. I think you need to absorb that information. Your teachers will chat to you about it. We gave you a worksheet that you can work through. Teachers, you can work through that worksheet, discuss it with them, compare the intermolecular forces. You're going to have to introduce the physical properties. I don't want to introduce physical properties with them today as well, because this was a lot of information to absorb. They need to think it through, need to absorb the information, compare the strengths of the intermolecular forces. And then you can look at boiling points, vapor pressure, and viscosity with them that results from the strength of intermolecular forces. So I hope you enjoyed the 2 days. And I think I enjoyed working with you people, even though I don't see you. I'm going to spend a lot of time with you next year. I'll be streaming lessons to you at your school next year. So you're going to get sick of me. You're going to see me every day, or whenever your timetable has signs on it. I'll be streaming lessons to you like I'm doing now, and I'll go through the matric syllabus with you. What I can't do is check up on you. And part of teaching is checking up on people, making sure they do their homework, and that is where you're going to have to be disciplined. Yes, you're going to have me to explain things to you. Yes, you might or might not understand me. The advantage you have, if you don't understand the way I explain things, and there aren't many people that don't understand how I explain things in science. The advantage of all that is you have your teacher right there. So, we will stop there for today. Thank you. I saw your message, Kensington. And thank you for those others that are saying thank you.